Je suis très content d'être ici. Je remercie Clément pour m'inviter à être ici dans le Collège de France. Et pour moi, c'est une institution qui est inimaginable à mon pays. Et c'est pour ça que je suis très content et comme on dit, envie de vous, les Français, pour avoir quelque chose comme ça, une institution comme ça. Bon, I had to switch to English because I think it's much better for everybody, much better for me for sure, and probably much better for you too. So I will start my talk today. This is a talk completely different, because till now and everywhere, I mean, biology is dominating everything, I mean, it's logical. But I will talk about something that is how to mimic biology without using biology, even without using organic compounds. So this is the subject of my talk is about how we can make shapes and texture characteristic of biological made structure, right? But without using the halo of life, which is very useful sometimes, and without even using the organic compounds, okay? First of all, I would like to introduce my colleagues. This is an investigation that started many years ago. I will tell you later why. And there are many people who helped me in this year. So Salvador Dominguez Bella, who was the first student working with me, then Emilio Melero Garcia, now the Yemen, was a postdoc in my lab. And then Matthias Kellemeyer and Fabian Glaff and Werner Kunz from University of Regensburg. And certainly Stephen High and his team in the Australian National University. And now I have Gan San, is one of my current students. He's finishing the thesis. And Fermín Otalora is one of my co-workers that he will join me now in this for the next year. Also from Italy, from the University of Bologna, these people, Marco Montalti, Damiano Genovese, and Giuseppe Fallini, they have a wonderful technology to measure pH at a very high resolution. I will tell you something later about that. And then also Joan from University of Alabama. He's working something I will not tell about everything, but Joe is working in the interaction of amino acid and other compounds with the structure I will talk about. Marc Van Swilling is from the Institut de Physique de Globe de Paris. We are also working in trying to imagine how silica, and what was the role of silica, the silica played in the early days of this planet. And then recently, Helmut Kolfen will join, and his team will join also our group working on the application of the structure I will talk about. Let me start with the history of the planet. I mean, this is the history of the Earth. This is 4.5 billion years. So that means that, well, if we remove here the line, this very thin line of the PowerPoint, all the hominids disappear, okay? So here will be the P will be the dinosaur, okay? Here is where the first fossils, real fossils, and clearly fossil that have some backbones can be found, okay, 300 million years ago. And what we will talk about is how to detect life, not that life, but the life that probably appeared in the planet 3.5 billion years ago, okay? So we are talking about something that occurred many years ago. The problem of light detection is that there are very few, I mean, only just 4 ways four different tools to identify life, to detect life resonance. One is the isotopic signature for carbonaceous resonance. This is something that was very useful in the past, still is useful, but there is no clear evidence that we can detect life only using this technique. Then the chemical composition of carbonaceous compound. I mean, the kerogen forming the microstructure considered to be fossils, which is also a problem. I will tell you later about that. And the most important technique is the morphology. I mean, people try to identify the older remnant of life by using morphology. Yes, purely morphology. Why? Because these are microstructures found in the Archean times, Archean and or Proterozoic. So you have here this structure that have cetacean, which is very biological feature. You have helicoidal shapes. Okay, they are this tubular sectated structure too, and this structure that, I mean, you found this kind of structure in a rock, most probably you say, okay, this should be a fossil, should be the remnant of an organism, because the complexity is very high. Okay, maybe you remember also this famous claim from NASA that they found life in the meteorite, in the Martian meteorite found in Antarctic. So they claimed by five different methodology, but the most important one was the morphology. Is that, well, we found this kind of material, this kind of structure. This structure is complex enough, not to be produced by mineral, just mineral processes. So they cannot be really explained by non-biological processes. This is the idea. The people believe that complex shapes is something which is putative of biology. Okay, while in the case of crystal, because this is something that everybody had in mind, that there are two worlds of symmetry: the symmetry of the crystals and the symmetry of life. The symmetry of the crystal, the symmetry of the mineral, is a symmetry that is dominated by the straight lines, dominated by the polyhedra form for faceted polyhedra. Okay, while the symmetry of life is a symmetry in which you have continuous curvature. And people think that it is impossible that inorganic compound, mineral processes, natural mineral processes, are able to produce continuous curvature. In some way, this is true, because if we study in detail the symmetry of natural shapes, of course, if you have a crystal in which the morphology is dominated by the structure, okay, then you have a restriction of 32 point groups. Point groups of symmetry is the symmetry that give you the shape, right? So there are 32 point groups, maybe 35 if you consider quasi-crystal, okay? But this is not all that we have. This is not possible to have all the kind of symmetry. While in the realm of life, you have sinuous shape, you have continuous curvature, you have unrestricted symmetry, okay? So this is certainly, in principle, this is true. This is something that should tell us that if you found something with complex morphology, with continuous curvature, then this should be something for sure related to life. But in the question is, well, are the abiotic precipitation mechanisms producing material with morphology with continuous curvature, characteristic of primitive life? And the answer is yes. There are many. Actually, there are many. But to be relevant to the problem of light detection, they had to, all this possible way to mimic light morphology had to fulfill three conditions. The first one is that they must be the result of self-assembly process, because otherwise we can use many of the techniques that we use normally in the lab in order to produce material with mimicking life. Okay, so we can make a continuous curvature of crystal, just taking a surface with a curvature, and then we have epitaxial growth on this surface. Okay, but this will be something induced, right? It's a morphology induced by the process in which we create the material. However, if we are looking for something that appears by a natural process in the planet, then we have to look for some self-organized process, self-assembly process. Then they must be fully inorganic. Why? Because if we are talking about the detection of the first life, okay, then we should consider that there was no life, and therefore there was no organic compounds, not organic compounds derived from life in the planet. Okay? So we should look for something which is purely inorganic. okay? Or just purely inorganic with some very simple carbon-made material, okay? So, but in principle, we should not consider any kind of organic material, because we're using organic material. I mean, this is shape made in our laboratories, using calcite and induce the morphology and the growth of the calcite by proteins, okay? So it's possible to make very complex shapes with this mechanism, but you need to use amino acid, you need to use protein, I mean, you need to use organic compound derived from life, okay? So this is, we had to avoid this. We need to look for other things. And then the third one is, must be geochemically plausible, because there are many different ways that I told you. There are ways to do, is pattern controlled by fluid structure. You can make fractal structure with complex morphology. You can use mesoscopic phases, liquid crystal, as we showed this morning. We have a beautiful talk about this. Then you can use diffusion reaction systems such as leaching and precipitation. There are many ways to do it. But in order to apply this to detect life, okay, we need to have something that is geochemically plausible. We cannot expect that something which is not geochemically plausible will be able to make a structure that we can use as an alternative for life detection. Okay, so I focus on silica. And why silica? Because silica is weaker in Earth. This is something that is everywhere. No? And in addition, silica play a very important role in the Earth planet before the emergence of life. And actually, this is the part of the project I will develop in the next few years. Is what was the role of silica in a lifeless planet. Okay, but now we'll focus on detection, live detection, and then I will tell you mainly about silica biomorph. If I have time, I will talk also about silica. Okay, silica biomorph is a structure that are created, but a very simple way. The only thing you have to do is to perform the precipitation, I mean, to create a supersaturation in calcium carbonate, the barium carbonate, or strontium carbonate. It's an alkaline earth carbonate in the presence of silica at high pH, alkaline pH, at pH between 9.5 and 11.5, okay? If you perform this experiment, which is extremely easy to do it, there are two different ways, basically. One way is to take a solution of with silica-rich solution, pH 10.5, and then you allow the CO2 from atmosphere to go to the solution, and then at that pH, most of the CO2 is in the form of carbonate, and then you mix this with a solution of barium or strontium, and that's all. This is a very simple experiment. You produce the form I will show you later. There is another way to do it, is to use a silica gel, I mean, to prepare a silica gel pH 10.5, and then after gelification, you pour on top of the gel a solution of the barium chloride or calcium chloride or strontium chloride, and then the salt diffuse across the gel and then form inside the gel the silica biomorph. The structure are this one, okay? So this is the structure I'm talking about. You know, this is extremely complex for many years. And I discovered this in my thesis, and for 10 years or more, from 15 years maybe, it was very difficult to publish because the referees always say you have a contamination. And actually, it was a pity, you know, because it was not published, not accepted for publication. But also, we were very happy because that means okay, they look like, okay. This is actually the form. They are formed with continuous curvature, okay, and these are the facts. I mean, I will just make a resume of an abstract of the fact related with this material. So the X-ray diffraction infrared spectroscopy will show that is a composite material made of two different phases. A crystalline phase is a barium carbonate or calcium carbonate or strontium carbonate, and then an amorphous phase of tetrahedrally coordinated silica, and the concentration is very small. I mean, it's not a very high concentration. The concentration about 2-3% of silica. Mostly is crystalline carbonate. So the EDX10 and the FS10 and dissolution experiment that prove the existence of an outer skin of silica that you can see here. This is an experiment, very simple experiment in which we have the biomorph, and then we pour on the biomorph a slight acid, formic acid, to do a slow dissolution of the carbonate phase, and you can see that the carbonate dissolve, and then you have a phantom that mimic the morphology of the previous material, right? Then the crystalline phase is made of nanocrystals. So these are made, this structure, which are very complex, with this curvature, continuous curvature, difficult to explain how they form. They are made by millions of nanocrystals. They have, the nanocrystal have orientational coherence, right? But not translational symmetry. Okay, so you have all the nanocrystals are co-oriented one each other, okay? But there is no translation symmetry, just pure orientational symmetry. And then the morphology is pH dependent, so at lower pH we have only fractal growth, okay? And a higher pH, then we have the morphology displayed by the complex shape with positive and negative Gaussian curvature. This is important, the morphogenesis is independent of the fluid dynamics. So we can have exactly the same morphology in gels and in solution. So the fluid dynamics that in principle could play an important role. Actually, you can have the same kind of shape with manipulating the fluid dynamic, right? This is not related to this. So here the structure grow and the shape is controlled by the very growth of the structure. And then the growth kinetic is controlled by reaction. So this is the growth rate scale with time, okay, not with the square root of time. That means it's not diffusion controlled mass transport. And then, well, this is only orthorhombic carbonate create morphology. This is something that was true till 4 months ago that we discovered that also monohydrocalcite is able to do that. So now we know that aragonite type of structure and monohydrocalcite both forms biomorph. So the definition of the biomorph is that the silica carbonate structure that are cell assembled, nanocrystalline aggregate that show differential morphology of constant either positive or negative curvature. And they are abiotically produced, but mimic remarkably well the morphology of living organisms and also the texture. So I will focus today on the morphology, but the texture is also amazing how silica is able to mimic the structure of biominerals. Okay, there are two morphological routes for the biomorph. The first route is dilation symmetry, and the second route go to rotational symmetry. In the first route, we always start with a single crystal. Okay, so the first thing that form is a single crystal, in this case of aragonite type structure. So these are the pseudo-hexagonal twin of the aragonite structure. And then the crystal is a single crystal, and a single crystal have the symmetry of the pure aragonite, right? But this, because of the existence of the polymeric phase of silica, then the crystal start to split, okay? And then by continuous splitting with non-crystallographic branching, then form the fractal structure, coliform type fractal structure. This is a mechanism from many years ago, by Kate Padding. This is the mechanism in which you can see here the pyramidal phases of the barium carbonate. So you have the prismatic phase here, it's the hexagonal prismatic prints here, and this is the hexagonal bipyramid, okay? And then when the structure, the crystal grows, okay, then it start to split the tip, okay? And you can see there is no non-crystallographic branching. And this non-crystallographic branching is the one who produce, this fractal structure, colorful-like fractal structure that from outside look like globular, yeah, but inside have this crystallographic fractal structure. And that's all for pH when you work at pH below 10, right? But if you go at pH higher than 10, then what happens is that there is a fibrillation of the growth from. So the growth from break and then produce not just continuous splitting of crystal, I mean the crystal growth process, but start to nucleate in the growth from start to nucleate. So you have continuous nucleation of crystals, and this is I call fibrillation, and this is the reason why you can adopt in principle any morphology, right? Because as soon as you break the symmetry of the starting single crystal, then you are completely free to make any shape, the possible shape with this growth. Okay. This is what I told you. So you start to have with crystal growth, but then in a certain moment there is new nucleation process. Okay, that appear in the from of the structure. So this is how the crystal look like. So you have this nanorod, okay, nanorod material. I will explain you how we think that this structure form, okay. But in principle, you have nanocrystal with 200 nanometers in length and about 40 nanometers in width, and this is coated by silica, right? And then you have this co-orientation of the crystal. Always the crystal are co-oriented one each other. So how the crystal form? Well, in principle, if you have one of these two-dimensional lamella growing, okay, and the single crystal is in the center of the lamella, then the final form will be a disc, obviously, because you have a radial growth, okay, and this radial growth, you have similar, identical velocity independent of the angle, right? And therefore the final shape will be a disc. However, if we observe the phenomenon of with the optical microscopy, then you can see that there are some singular points in this disc, growing disc. Okay, this singular point in which the structure stops to growth, okay, and then produce this kind of shape. Okay. So there are different places there. What happens in this singular point? What happens is that you have the curling of the structure. So the structure is growing radially, and in this singular point, the structure curl. Okay? So this is what happens is that there's a curling of the structure, and then with the structure curl in that particular point, then there is no more radial growth. So they produce a curl, okay, that this curl propagates across the lip like a wave in the surf. Okay, it just propagate across the lip of the structure. You will see now. So this is the curling. Okay, when the curling occurs, they propagate across the lip of the structure. So there is no radial growth, no more radial growth. Okay, but this is a propagation across the lip of the lamella. Okay, so we have the growth velocity of the lamella, the radial growth of the lamella, and then we have now two other velocity. Okay, the velocity of the propagating curling. This one and this one. Okay, so we have this velocity. We have the degree of curvature. I mean, it could be very large, very high curvature or very small curvature. Okay, and then the curling could be left or right. Okay, so with 4 parameters, let's say actually 3, we consider this rate of velocity. Okay, with 3 parameters, you can explain all the morphology that we found in this silica biomorph. So the first one, for instance, is imagine that you have something is growing as a disc, and then you have 2 curling points here. Okay, and these 2 curling points are of different chirality. That means both are up or down. Okay, so one left and the other one right. Okay, so what happens is that you have the 2 points, the 2 curling points, and when they propagate, so they form a leaf or a cardioid, maybe it's better to show to see a video. So you can see here on the left, so you have the 2 calling points here. They are propagating across the leaf of the structure, and then when they just meet on each other and stop the growth. Okay? So this is displaying the leaf-like shape. This is characteristic of biomorph. Here we have the same thing, but then now one of the curling is up and the other curling is down. Okay? So what we have, you see, this is in focus, this is out of focus, this is up, this is down, okay? And then they are propagating, you can see there, and when they meet, they twist, okay? So this is the origin of the twist, and this is why we can find this helicoidal structure in the silica biome. Okay? Now, we have exactly the same thing here. So they are, both are left or both right, the curling, okay? The similar degree of curvature and the velocity of the propagation is similar to the velocity of the radial velocity, right? So now, if we have the same parameters, but the same value of the parameter, but then the velocity of the propagation is much faster than the radial velocity, then what happens is you have the curling, but the curling of the ring itself. So this is the what we call the braid. Okay. So you have here there is no more radial velocity, so you have the velocity. I mean the twisting of the the 2 curling. Okay. And then here is something which is very similar to some, actually to the oldest proposed fossil in the planet. We call them worms because it's exactly the same thing, but one of the curls have a radial curvature much higher than the other one. And then the structure is like this. Okay? So with this curling, we can really explain all the morphology that we found in silica biomorph. So this morphology that are very complex, but this mechanism of curling is extremely powerful from the point of view of morphogenesis. So morphogenetically, it's a really powerful mechanism. But life never used. But life never used the will also. So it means nothing, right? But I was asking many friend biologists, and then apparently never used such a mechanism, which is very powerful. So the mechanism that for instance, we explained that this mechanism explains the absence of chirality that we observe, and why all the laboratories trying to induce chirality in this structure, they fail. We fail also because we were trying to use small molecules to induce chirality in something which is mechanistically is a much higher scale. So maybe using very large molecule it will be possible to do it, right? But not with a small one. So this is the formation of the twisted sphere and the genetic twisted surface. All this is explaining by this simple mechanism. So now the problem of primitive life detection. This is something could be related to the detection of the oldest life in the planet. Well, because in principle this could be just a curiosity. I mean, this is make form that look like biological. That's all. I mean, it's a curiosity, nothing more. But the point is that these are the structures I showed you before. This is our microfossil, putative microfossil, and maybe real microfossil, right? Found in chairs. So they are found in chairs, in silica, right? And these are a structure that we made in the lab. So these structures we made are mimic extremely well the morphology. For even this Western Burgundy, which is extremely complex, it is made by a number of leaves. So this is something that you can make in the laboratory easily. Okay. So in principle, this is true. This is mimic very well. But one of the important thing is that all the microfossil the oldest microfossil in the planet has been found in chairs. Chair is silica. It's a rock made of silica. So, and the silica, as I told you, you know, the silica, for this structure to be relevant for the problem of light detection, the two conditions we have to fulfill, one is the self-assembly process. We know that this is purely self-assembly process, and this must be geochemically plausible. And this is you want to explain silica, I mean chairs in the planet, in the last 60 million years, mainly is the chair is made by silica secreting organisms, shells of silica secreting organisms. But if we're talking in something, you know, in the Archean, you know, here, so there was no life for sure, and for sure no life secreting, I mean, with biomyelinization process, so was not invented yet biomyelinization. So therefore, we need to explain silica in the origin of silica in other way. And one of the way is this is the solubility of silica as a function of pH. So until pH 11.3 is basically there is no variation of concentration solubility with pH. It's about 200 ppm, all right? But above this pH, immediately you start to have the first and second deprotonation of the silicic acid, and then it forms this strong dependence on solubility, and then it is very easy to explain the precipitation of silica if you start with a high concentration silica solution, it's a sea, a lagoon, you know, a pool, and there is a small chain of the local pH. So this is a way to produce, and that way will be the way in which, you know, I made the silica biomorph in the lab. So the chemistry is very, very similar. And in addition, I don't know if you have here. No, I think it's not here. But in addition, the oldest fossil in the planet, they are also made of barium. So this was barium there, and barium is the other alkaline earth carbonate that I have in the experiment. So that the chemistry it's not just the morphology; it's that the chemistry was also similar to the chemistry in which the rock, I mean, the chemistry producing the rock in which this microstructure considered to be the oldest fossil are embedded. Okay. So actually, you look for the protocol for recognition of Archean fossils, microfossils. Okay, there are a number of criteria that all them are fulfilled by this biomorph, and we have the problem was that the putative microfossil should be composed of kerogen, and this is the work that we made with Stephen High, my colleague from Australia, in which there was well known that you have iron carbonate, you know, and then you produce the disintegration of the iron carbonate, then it is possible to create, it's a way to create organic compounds. So what we did is to start with mixture of phenol formaldehyde, which is easy to explain in the early days of the planet, to have this kind of compound due to serpentinization. And then we made the biomorph in the presence of this simple material, these simple organic compounds. So they absorb on the silica biomorph. Then we heat to 350 degrees, and then we form kerogen with the material. So we just, in some way, we coated this, or they was self-coated with the organic compound, and then we create the kerogen. And then when we made the Raman spectra of the biomorph, coating with organic compound in that way, then, you know, we demonstrate that the Raman spectra is the same one that the Raman spectra observed for the putative microfossil found in Archean rocks. So this is the result that we published, and at the very beginning, I mean, when we published this, it was a big controversy. I think that now everybody realized that we made a good contribution in the sense that we say, oh, we are not saying that they are not biomorph, they are not fossil. We are just saying that this is, you have to be careful. You know, we have to be careful. And actually, our conclusion is that morphology does not contain inequivocal genetic information. So we cannot use morphology alone, and we cannot use morphology and chemical composition in terms of organic compounds alone for live detection. And actually, I think that today, very few people is able to publish something based, a claim for live detection using these two tools, okay? So this is interesting, because some people could say, okay, so you see that, you say that morphology does not inform about biogenicity, and then the answer is no, because people think that we consider this to be a fossil because of the morphology. But this is not morphology. This is, people forgot about that. Actually, we know that this is a fossil for someone who was professor of this Collège de France, Le Baron de Cuvier. I think that he was professor here. And the Baron de Cuvier is the one who invented the comparative anatomy. It is actually because of comparative anatomy, not because of morphology. Because comparative anatomy, that we know that this is biogenic. Okay? Why? Because the problem of light detection, of early light detection, is that, this is, I don't know if you know this book. It's a book of Stephen Jay Gould, beautiful book, wonderful writer. And this is limestone of Marrakech, because if you go to Marrakech, there are people there selling fossils, and they made the fossil. They made very well. Okay? So it's just to tell you that it's not morphology, it's comparative anatomy. And this book, Stephen Jay Gould, go to Morocco and then start to analyze the fossil made by Moroccan people, right, to determine why they're fossil, they are not fossil. Okay? Just by, the only way to do is by comparative anatomy. Pure morphology is not enough, okay? And, this is a paper, for instance, from the Porter and Bensedar. There are people that are now, identifying and studying in detail and then recognizing something that in principle could be considered to be biological in origin. Now people study in detail, in order to really know if this is a fossil, real fossil or not. So I think that this is interesting. The morphology cannot be used. And the main problem is that we are talking about early life. We are talking about something very small and very simple. So we cannot really use comparative anatomy. There is no way to use. Therefore, this is the problem. This is why, to me, in order to use morphology as a criterion for biogenicity, we need to wait until biology defeats physics, okay, in evolution. So as soon as you have something completely not made by biology, then I think that we can really use morphology as a criterion for biogenicity. Okay. Now, this is one point for people who are not still understood. This is, there are two spheres, and then over here planted from three. Okay, this is very simple. You can use, but people use this for fractal, for instance. People measure the fractal dimension. That is nothing more than this. The only point is that fractal dimension. This is known and it's a fraction. Okay, so certainly, morphology cannot be used. You have to be very careful. Not only comparing biology with non-biological objects, it's comparing also a non-biological object. It's very difficult to and very dangerous to use pure morphology to imagine and to know morphogenetical process. So, what is the chemistry behind this material? This is the chemistry. The chemistry, basically what we have there is the coupling between two different chemical processes. We have, in one way, the silica precipitation and then the carbonate precipitation. And then here is this is why we have in between 9.5 and 11.5. Most of the CO2 is in the form of carbonate, okay? And then you have the silica, as I told you, the silica after pH 9, the silica, start to increase dramatically due to the first and the second deprotonation of the silicic acid. Okay, so what we propose is that when the carbonate is growing, okay, so the carbonate is growing. This is the solubility of silica. So the carbonate is growing, and then the pH decrease to the carbonate precipitation, because when you precipitate the carbonate, then it produces hydrogen, and therefore you have a decrease of pH, right? And because of the decrease of pH, then the silica precipitate in the growth form, right? And then when the silica precipitate, then there is an increase of pH. And then the increase of pH then provoke a higher concentration of carbonate. There's the equilibrium shift to carbonate, and then still you have the precipitation of carbonate. Okay, so you have a cycle, okay, in which there is a continuous precipitation of silica and carbonate. I mean, the carbonate, which is the phase which is growing, okay, is the one who induce the precipitation of the, let's say, the silica, the additive that we use in order to modify the morphology. So this is a continuous process. This is why this is always working, and always working far from equilibrium, because it's something that continuously is happening in the growth form, okay? This is the explanation. I will not go into detail, but basically this is the explanation of why we have the precipitation of silica biomorph in this range of pH. It's because in the range of pH in which both the total CO carbonate and total silica, the variation with the total silica and total carbonate as a function of pH is not zero in none of the cases. Okay, in this range there is what the silica biomorph form, and in some way this support our hypothesis. The problem is that when we try to publish this, the referees say that yeah, you have to measure. This is interesting, but you have to measure, right? This is and to measure this in the growth form, because what we claim is that everything happened in the growth form. Why we know that everything happened in the growth form is because this experiment. This is another simple experiment, but very useful. We made the biomorph in solution at different stirring velocity. And then we found that even to 300 revolutions per minute, okay, you form the helicoidal and the worms form everything. So that means that you are stirring. This is something that the formation of the structure is something that occurs in the growth form. It's nothing related with the bulk, okay? So, but it was very difficult to measure until we found these people from Marco Montalti and colleagues from Bologna. So they are expert in the use of confocal microscopy and fluorescent dye in order to measure the pH. So they made a device in which using a fluorescent dye, we can measure the pH with a resolution of few microns, okay, and about 0.1, even less than 0.1 resolution in pH. Then this is the growth. This is a video with the growth of the biomorph. You can see that actually this biomorph is growing, right? So again, this biomorph is growing, and you have the chain of pH. I mean, it's just in this. Nothing happened in the bulk. It's just in the growth form. Okay, and if you look for this, and what we did is to measure the intensity of the green color here, intensity of the green color as a function of the angle, okay, and as a function of time, and then you put this in this contour map. You can see that, well, yeah, you can see that there are oscillation of pH in the growth form, okay? So this is a very tricky video. Actually, we have not yet published it because we are waiting to have we have another one, okay, and we're waiting to have a better one. The problem is we need to obtain just lamella, because as soon as you have a curling, then everything is broken. I mean, all the symmetry is broken, and then it's impossible to measure with accuracy, right? But this is something that I think is a very good proof that the phenomenon is a phenomenon in which is a chemical coupling between the precipitation of the two, the carbonate and the silica. This is a recent result that we have obtained, because till now we were only working with, we only have a barium carbonate and a strontium carbonate. This is interesting, you know, but we were trying to have the same behavior with calcium carbonate, and finally we found that with some experiment, it is absolutely reproducible. You can have, this is very interesting, because you have here the carbonate, you have calcite, okay, and then this is the gel, you have the calcite at the very beginning, then you have aragonite with a completely different morphology, okay, the biomorphic morphology, and then calcite again. This is what I asked you before this morning about, you know, how to explain this. This is the aragonite calcium carbonate, okay? So you can see the morphology, which is morphology similar to the biomorph, while the calcite is fibrous calcite, okay? So we have, this is a wonderful video, I think, because it's first of all, explain very well the morphogenetical behavior of the two different phases of calcium carbonate. So you have this aragonite growing as biomorph, and this calcite, you know, it's just 400 micron, one far each other, right? And calcite, just fibrous calcite, while in the case of carbonate, you have this wonderful behavior, okay? So this is interesting. We are studying this, and actually, this is part of the thesis of Garcia, and he also showed that not only aragonite, but also monohydrocalcite is able to form this. We are studying now to explaining, I think we will have very soon read the paper explaining the morphology of these two, the behavior of these two phases of calcium carbonate, so different one each other in terms of morphogenesis. Well, these are the conclusion. I think I have no time. Maybe it's time for some conclusion. Thank you very much.